Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 9 today, talking about hypothesis testing for population mean when sigma is unknown. In the last section, we talked about what to do when sigma is known. When the population standard deviation sigma is unknown, we substitute the sample standard deviation S in place of sigma. The sample standard deviation will be known once a sample has been collected. So in the case where sigma is unknown, you use the student's t distribution for the test statistic rather than the normal distribution. And assume that the population of interest follows the normal probability distribution. For example, the average cost of a hotel room in Chicago is claimed to be $188 per night. A travel agent thinks it is lower now. A random sample of 25 hotels resulted in a sample mean. Let's put a bar over that X of $177.50 and a sample standard deviation of $25.40. Test the appropriate hypothesis using an alpha equals 0.05 level of significance and assume that the population distribution is normal. Oops. Okay. All right, so step one is to identify the null and alternative hypotheses. The travel agent's claim was that the average cost is now less than $188, so that would be our alternative hypothesis. And then the null hypothesis would be the status quo, which is that the average cost is not less than $188. Step two, set a value for the significance level alpha. Remember that alpha equals 0.05 was specified for this test in a statistics class. Alpha will always be given. Step three, determine the appropriate critical value. Sigma is unknown, so we'll use a t-score. And since the sample size is 25, we will use 24 degrees of freedom. And since this is a one-tail test, specifically a lower tail test or a left tail test, the entire area for alpha equals 0.05 is placed on the left side or the lower tail of the sampling distribution. So there are a couple different ways to find the critical t-value. One way is to use table A3. So let's take a look at table A3 real quick. I've got it open right here. All right, so you go down to 24 degrees of freedom and then make sure that you're using the correct column. Since this is a one-tail test and alpha equals 0.05, we're going to use this fourth column here, going down to the row where the degrees of freedom is 24. I see a value there of let me circle it for you, 1.711. Okay, now we have to be careful because this is a lower tail test. Oops. We have to put a negative sign in front of that value from the table. Okay. All right, so here's the picture. Let me get rid of my circle there. All right, so I think that's the easiest way to find critical t-values. You can also use Excel using the function t.inv. So the way that works is you would go to an empty cell, open a blank worksheet, and type equals t.inv. And then in parentheses, you would put your level of significance, which for this problem is 0.05, and then your degrees of freedom. The Excel function returns the left tail critical t-score, which is negative 1.711. So Excel gives you the negative value because that is the t-score that cuts off the bottom 5% of the distribution. In other words, for this particular t distribution with 24 degrees of freedom, that value is the 5th percentile. There is one other way that I don't think I've ever shown you before. Excuse me while I try to get out of here. And that's to use a website called StatTrack. So the easiest way to find StatTrack is to open Google and type in T distribution calculator. You can see I've typed that before. So it comes up, even if you've never typed it before, I think it comes up in the top 3. So here's the link right here. I'm going to click on this. So the way this works, the random variable is the t-score. The degrees of freedom is 24. I'm going to leave t-score blank because that's what I'm trying to find. And then in this box at the bottom, I'm going to put 0.05. And then when I hit calculate, it fills in that t-score negative 1.711. So however you want to do that is up to you. Again, to find a critical t-score, I think the easiest way is just to use table A3. Just remember you have to be careful with your sign. If you're doing a left tail test, remember to put a negative sign in front of the score from the table. Okay. So you can see our rejection region there. We're going to reject the null hypothesis if our test statistic comes out to be less than negative 1.711. Otherwise, we will not reject the null hypothesis. All right, so now to calculate our test statistic, you use this formula, which is very similar to the one that we used in the last section. The big difference is you have S here instead of sigma. All right, so the notation here, T sub X bar is the t-test statistic. X bar, as usual, is the sample mean. Mu sub H0 is the mean of the sampling distribution, assuming the null hypothesis is true. And S is your sample standard deviation, and N is your sample size. So in this problem, the test statistic comes out to 177.50 minus 188, and then divide that by 2550 over the square root of 25. And I've said this to you before, if you want to put all of this into the calculator at once, just remember that you need parentheses around this quotient in the denominator. Oops. All right, so that comes out to negative 2.07. So now we compare our test statistic with the critical t-score. Since this is a lower tail test, it's kind of redundant to say one tail, lower tail. Just say lower tail. Reject the null hypothesis if your test statistic comes out to be less than your critical t-score. And I always recommend drawing the picture. I think that's the easiest way to figure it out. Just see if your test statistic lands within your rejection region or not. Here, negative 2.07 is less than negative 1.711, so we will reject the null hypothesis. Okay, and there's the picture that I like. So there's the rejection region that we saw a couple slides ago. The calculated test statistic, negative 2.07, clearly falls within that region. All right, so then the conclusion stated in a good English sentence that talks about this particular problem could go something like this. According to our sample evidence from 25 hotels, there is enough evidence to support the claim that the average cost per night is now less than $188. So it appears that the travel agent is correct. All right, so for p-values, you have to do one of two things. You either have to, hang on one sec. Okay, I just noticed that I forgot to update the reference to the table. So we're using, the table we're using is called table A3. So I wanted to update that for you. All right, so again, to find a p-value, you have to do one of two things. And I'm going to tell you which one I prefer. And it's not this one. All right. If all you have is the table, then the best you can do is to get an interval where the p-value is located. In other words, you can say the p-value is less than this number or between these two numbers, uh, but you will not be able to, for example, approximate the p-value to 4 decimal places just using the table. All right, so the way that works with the table is like this. In the last example, the t-score was negative 2.07. So we need to look at the table and find the critical t-scores that bracket 2.07 in the 24 row. And there's the wrong reference again. That's supposed to say table A3. All right. So the p-value will be between the two probabilities shown in the corresponding column headings. Okay, so I've pulled up table A3 to show you what we're talking about here. So if you go to the 24 degrees of freedom row, let me bring up my pen here, and look for the two closest values to 2.07. So what I see here is a 2.064 and a 2.492. In other words, one of those is less than 2.07 and one is bigger. Those go with one tail areas of 0.025 and 0.01. All right, so what I'm going to do now is switch over to my tablet. I've drawn you a picture of what that means. All right, so what the table is telling me is that if I look at negative 2.064, remember this is a left tail test, the area to the left of negative 2.064 is 0.025. And then the area to the left of negative 2.492 is 0.01. Since negative 2.07 is between those two values, that means that the p-value, which is the area to the left of negative 2.07, has to be between 0.01 and 0.025. So the best you can do, again, if you're using table A3, is to find bounds for the p-value. Okay, so in this case, the p-value is between 0.01 and 0.025. Okay. Now, since we have access to technology, though, you can actually nail down the p-value to, 4 decimal places, which is usually what they ask for example, in the homework. So let me switch back here. I'm going to bring up StatTrack again. All right. So the way this works is you have to fill in any 3 of these boxes. So when I was looking for a critical value before, I left this box blank and I filled in this one. Now what I'm going to do is I'm going to fill in my test statistic, negative 2.07. And when I click calculate, the number that's going to fill in the bottom is my p-value. So it's telling me the p-value is 0.0247. All right. So let's see. Going back here. Okay, we're done with that part. Okay, so just referring back to getting it from the table, that information that the p-value is between 0.01 and 0.025 would be enough to say reject the null hypothesis. If you want the exact p-value, then you can either use StatTrek the way I just showed you, or you can use Excel. So this slide is explaining how to use Excel using the t.dist function. So the way that works is you go to a blank cell, type in equals t.dist. X would be your calculated test statistic, negative 2.07. Your degrees of freedom for this problem is 24. And then for this last thing, always put true. I have still never encountered a situation where you put false there for a continuous probability distribution. So for this problem, if you enter t.dist and then negative 2.07, comma 24, comma true, you get the same p-value that we just got from StatTrek. All right, here's another example. The claim is that the average person in the US watches 34.5 hours of television per week. Suppose viewing data is recorded for 10 people and the sample mean is found to be 39.6 hours and the sample standard deviation is 16.4 hours per week. The following slides show the steps to complete this hypothesis test. Step 1, identify the null and alternative hypotheses. So this time the claim was that the average time equals 34.5, which means that claim will become the null hypothesis, and the alternative hypothesis will be that the mean is not 34.5. So in other words, this will be a two-tailed test. Next, we set a value for the significance level alpha. They didn't give that on the previous slide, but now they're saying, suppose that alpha equals 0.02 is chosen. Step 3, determine the appropriate critical values. Since sigma is unknown, we will again use a t-score for alpha equals 0.02 and 9 degrees of freedom, since our sample size is 10. Since this is a two-tailed test, the alpha equals 0.02 is split equally into two tails. All right, so again, you can find the critical t values from table A3. You know what, from now on, if you see any reference to table 5 in Appendix A, we call that table A3, all right? Or with Excel's t.inv.2t function. So the 2t stands for two-tailed. Let's bring up the table real quick so we can just make sure that we're able to find what we need from the table. Because again, I told you that I think the easiest way to get critical values is from the table. All right, so this is a two-tailed test with alpha equals 0.02. So we're going to use the second column. Going down to 9 degrees of freedom, I see a critical value of 2.821. And since this is a two-tailed test, that means we have two critical values, plus and minus 2.821. All right, so let's get rid of that. All right, so this is what your rejection region looks like. We're going to reject our null hypothesis if our calculated test statistic is either less than negative 2.821 or greater than 2.821. All right, so here is the calculated test statistic, 39.6 minus 34.5 divided by 16.4 over the square root of 10. Don't forget, if you when you put this in the calculator, to put parentheses around that quotient on the bottom. So that comes out to 0.98. So now we'll compare the test statistic with the critical t-score. For a two-tailed test, reject the null hypothesis if the absolute value of the test statistic is greater than the absolute value of the critical t-score. And again, I think the easiest thing to do is just look at the picture. Since 0.98 is not greater than 2.821, we will not reject our null hypothesis. So let's go to the picture. All right, here it is. So you've got critical or rejection region down here. You've got rejection region up here. 0.98 is falling in the middle. Okay, so that means do not reject the null hypothesis. So our conclusion would be that the random sample of 10 viewers does not provide sufficient evidence to reject the null hypothesis. So we have no evidence to conclude that the average is not 34.5 hours per week. Okay. All right, so I just realized that they did not show how to get the p-value in this example. So let's do that real quick, and then we'll be finished with this section. Oops. See, we'll be finished with this section. All right, go back. There we go. All right, so I'm going to go to StatTrek. We're going to change the degrees of freedom to 9. And let's see, our t-score was 0.98. Okay. Now, I need to be very, very careful with this. Okay, that number right there is not the p-value. Let me show you how to get the p-value from this number. So for that, I'm going to go over to the tablet. Give me just a second to get this set up. Okay, so I've gone ahead and drawn a picture of what that number that we just found means. The 0.8237 that we got from StatTrek represents the area to the left of t equals 0.98. And then in my picture, I've highlighted for you which area the p-value represents. So remember, the p-value in any problem represents the probability that under the null hypothesis that you would get a sample that's as extreme as the one you found. So for a two-tail test, extreme means in either direction. All right, if the mean viewing time for our sample had been a lot higher or a lot lower than 34.5, we would have rejected our null hypothesis. So in this case, since the area to the left of 0.98 is 0.8237, that means the area to the right of 0.98 is 1 minus 0.8237, which is 0.1763. Okay, so that area over there is 0.1763, and this area here is also 0.1763. That means our p-value is 2 times 0.1763, which is 0.3526. Okay. So again, what that means is in a world where the population mean really is 34.5, the probability of getting a sample at least this extreme is over 35%. There's over a 35% chance of getting a sample this extreme. So that is hardly strong evidence against the null hypothesis. This would definitely be a do not reject the null hypothesis. Not strong enough evidence to conclude that the mean is not 34.5. And that's going to do it for section 9.3. We've only got one more section to go after this. And so we'll see you next time for that.